Hello everyone and welcome to lesson number 5, Trigonometric Identities. Just a warning before we get started, I personally do think this is the most difficult lesson in the entire course. And for those of you who like a challenge, you're going to be pleasantly surprised. Here we go. In mathematics, an identity is a statement that is true for all values of the given variable. If there are any restrictions, they should be stated, just like we did in Unit 1 when we learned about restrictions. So let me just take a moment to motivate what an identity is. But first, I'd like you to consider the following. Say we have a simple equation, 2x equals 4. If I were to ask you, what values of x makes this equation true, you would solve for x. So dividing both sides by 2, we get that x equals 2. So notice this equation is true only when x equals 2. That's an equation, but here's the difference between an equation and an identity. Identities are true for all values of the given variable. So imagine if 2x equaled 4 for all values of x. Clearly it's not, but if it was, this would be an identity. So in the table below, you're going to see a list of identities that you need to know in this course, and we'll be using them frequently throughout the lesson. So feel free to refer back to this table if you need to at any point. So remember, these identities are true for all values of the variable. The first one is tan theta is equivalent to sine theta divided by cosine theta. And I just want to mention that our restrictions will be wherever the denominator is 0. So for example, in the first one, because we're dividing by cos theta, we require that cos theta cannot equal 0. And that's going to be true for all the others. So I won't repeat them, but just keep in mind the restrictions are whatever. The restrictions are there to ensure that we do not divide by 0. The second one is cosecant theta is equivalent to 1 over sine theta. We actually learned this one back in lesson 1. This is one of the reciprocal trigonometric ratios, and you'll see the other two appear as well. Secant theta is equivalent to 1 over cosine theta, and cotangent theta is equivalent to 1 over tan theta. Next up, we've definitely seen this one before, and I know I proved it with you in the first lesson of this unit, but when you take the sine of an angle and square it and add that to the cosine of an angle squared, that always equals 1. Please note that there are no restrictions for this one because there is nowhere where you divide by 0. And the next two are brand new. 1 plus the tan of an angle squared is equivalent to secant of the angle squared. And finally, 1 plus the cotangent of the angle squared is equivalent to cosecant of the angle squared. These also have no restrictions. And I need to mention one thing about notation. We're going to use this notation for the remainder of the unit. Please note that when you see something like this, sine squared theta, that's the same thing as saying sine of angle theta all squared. This is sort of the mathematician's lazy way of writing sine theta squared, but please recognize it means the exact same thing. It's a little notation that saves us from having to write the brackets every single time. What we're doing in this lesson is proving that an identity is true. So you'll be given an equation, and we'll be proving that that equation is in fact an identity, meaning both sides of the equation are true for all values of the independent variable. Here's how we prove that an equation is an identity. We begin by choosing one side of the equation, so either the left side or the right side, and once you pick one side, you have to stick with it. You're going to keep working with that one side of the equation, simplifying it until it looks like the other side. To help you do this, you're allowed to use any of the identities in the table above. You would substitute them in as required. So by the way, you can assume that all of the identities in the table above are true, and you can use them at any point without proof. Another trick you can use to help you prove that something is an identity is the mathematical trick of adding zero. When you add zero, you're really just adding and subtracting the same thing. For example, adding and subtracting 5. But as you'll see, this can be a trick to help you make an expression look like something else. We used a very similar trick when we were completing the square back in Unit 3. And finally, another trick you can use is multiplying one side of the equation by 1. For instance, multiplying by 5 over 5. This can be done as well to help you manipulate an algebraic expression to make it look like something else. And we've done this several times as well. We actually did it back in Unit 3 when we were rationalizing a radical expression. Now you may be wondering, why are you allowed to add 0 and why are you allowed to multiply by 1? The reason is adding 0 and multiplying by 1 don't change the value of the expression. They're still equivalent, which is why we're allowed to do it. All right, before we move on, one thing, when you're proving that something is an identity, you can't work with both sides. You have to work with just one side. And this is actually what makes proving identities completely different from what you're used to, but we're going to see how it's done with several examples. So let's get started. First off, I'd like you to show that in any right-angle triangle, prove the first identity, which is tan theta is equivalent to sine theta divided by cosine theta. In order to help us prove this, I'm going to sketch an arbitrary right-angle triangle. I'll pick an angle, label it theta, and I'll label my sides A, B, and C. So in order to prove that tan theta equals sine theta over cos theta, we need to pick a side to work with. I'm going to pick the right-hand side. So the right-hand side, RS, equals sine theta divided by cosine theta. And now, using the picture to the left, we can come up with expressions for sine theta and cos theta respectively. So for instance, sine theta would just be opposite over hypotenuse, which is equivalent to B over C. Similarly, cosine theta is equivalent to adjacent over hypotenuse, which would be A over C. Let's substitute those into the expression above and see what it simplifies to. So therefore, the right-hand side is equivalent to sine theta, which is B over C, divided by cosine theta, which is A over C. We've definitely simplified something like this before. What you can do is, instead of dividing by the fraction, you're able to multiply by the reciprocal, which we'll do. So that's B over C multiplied by C over A. Notice now that the C's cancel out, leaving you with B over A. But wait a minute, what is B over A? B would just be opposite to angle theta, so let's go back to the picture for a moment. This is the opposite side, and notice that A is the adjacent side. Hey, what's opposite over adjacent equal to? Hopefully you recognize that that's the expression for tan theta. And there you go, everyone, we've proven this. So to conclude, we've shown that, therefore, the left-hand side is equal to the right-hand side. When you're proving an identity, always write a therefore statement where you conclude that left side equals right side. And that's that. That's how you prove identities. Well, let's try another one. Okay, in example 2a, we're going to prove that 1 minus cosine x squared divided by sine x is equivalent to sine x. When you're proving an identity, you need to pick a side. So here's my advice. I'm going to recommend that you always choose the more complicated side. And the reason is, in math, it's often easier to go from something more difficult to something easier, rather than going from something easier to something more difficult. So because of that, what I'm going to do is pick the left-hand side. So we always start off by writing out the side that we choose. And now we somehow have to show that the left side equals sine x. So one trick that you're allowed to do is substitute any of the identities from the previous page. And let me just ask you, where have you seen 1 and cosine squared x in the same equation? Well, let's go back to the previous table. And I think you'll see that the fifth identity has what we're looking for. In this one, sine squared theta plus cosine squared theta equals 1. What happens if you rearrange for cosine squared theta? So notice here that if you bring the sine squared theta to the other side, we get that cosine squared theta equals 1 minus sine squared theta. You're allowed to do that. You can work with any of these identities because they're already assumed to be true, and you can manipulate them as needed to help you prove the identity. So what I'm going to do is substitute cosine squared theta for 1 minus sine squared theta. I hope that was clear, but you're allowed to use anything from this table to help you out. So let's do that. All right, so here I had x instead of theta. Don't worry, it's the same idea. So we replace 1 minus cos squared x with sine squared x. And we're almost there. We have to show that sine squared x over sine x equals sine x. Now, what does it mean when you square something? Whenever you square something, it just means to multiply the thing by itself twice. So sine squared x is equivalent to sine x multiplied by sine x, and that's all divided by sine x. And just like in Unit 1, when we were simplifying, you can cancel out one of the sine x's with one of the sine x's. And therefore, the left-hand side simplifies to just sine x, and that's your right-hand side. So we're done. Therefore, left side equals right side. Okay, everyone, so this is the style of proving identities. I know it seems weird, it's going to seem different, but please hang in there. We're going to have to do lots of practice until we become more comfortable with this. Let's do another one. In part B, we're going to show that cosine x multiplied by tan x is equivalent to sine x. So which is the more complicated side? I hope you agree that it's the left-hand side. So always begin by writing out the side that you want to work with. And now we somehow have to show that cosine x multiplied by tan x is equivalent to sine x. What I'm going to do to help me out over here is I'm going to use the first identity in the table. Recall that tan x is equivalent to sine x divided by cosine x. We actually proved this in example 1. And this is multiplication now. Remember, cosine x is over 1, and when you multiply fractions, multiply numerator by numerator, and denominator by denominator, you're also able to cross-reduce like this. This was something we did back in Unit 1 when we were simplifying rational expressions. So what are we left with? We're left with sine x over 1, which is just sine x. And that's your right-hand side. So we're done. Therefore, left side equals right side. So the last two that we did were examples of easier identities. We're now going to do some medium identities. Let's move on. In example 3, we want to show that 1 over 1 minus sine x take away 1 over 1 plus sine x is equivalent to 2 tan x divided by cosine x. Which side should we start with? Well, I'm going to pick the more complicated side, which I think is the left side. Okay, so how do we deal with something like this? Here's my tip to you. Notice that we have two fractions on the left side, and on the right side we have one fraction. So we somehow have to make two fractions into one. How do you make two fractions into one? Well, what's the operation between the two fractions? We're subtracting them. And the only way to subtract fractions is to make sure that they have a common denominator. So we're going to find a common denominator, which is exactly what we did back in Unit 1 when we were adding and subtracting rational expressions. So to help you out here, I'm going to put brackets around the two expressions in the denominator. And you may recall a trick that we did back in Unit 1 was to just multiply each fraction by the expression it was missing. So here's what I mean. We're going to take the first fraction, and we're going to multiply the top and bottom of that fraction by what we need. What we need here is a 1 plus sine x. This is that mathematical trick I told you earlier of multiplying by 1. We're going to do the same thing with the other fraction. So we have 1 over 1 plus sine x. And we're going to multiply the top and bottom of the fraction by the other denominator. So we multiply the top and bottom by 1 minus sine x over 1 minus sine x. Give me one moment, everyone. I need to make my writing a little smaller because if I don't, I'm not going to fit this on one page. That's the beauty of working on a tablet. Okay, so just like what we did back in Unit 1, we're going to multiply numerators and denominators. So 1 multiplied by 1 plus sine x is just 1 plus sine x over the product of 1 minus sine x multiplied by 1 plus sine x. Remember back in Unit 1 I told you not to FOIL the denominators? Well, for now we're not going to do that as well. We may have to later, but we're going to keep with the same rules like we did before. As for the other fraction, we multiply numerators and denominators as well, so that gives us 1 take away sine x over 1 plus sine x multiplied by 1 minus sine x. Alright, so now that we have the same denominators, I'm going to write this as one big fraction. So that's 1 plus sine x take away 1 minus sine x over the one big fraction of 1 minus sine x multiplied by 1 plus sine x. Just like what we did back in Unit 1, we're going to simplify the numerators. So let's go ahead and collect like terms in the numerator. We have 1 plus sine x, take away 1, take away negative sine x, which turns into positive sine x, all divided by our common denominator of 1 minus sine x multiplied by 1 plus sine x. Okay, look what happens in the numerator. The 1's cancel out, so 1 take away 1 goes to 0. You can collect like terms now. Sine x plus sine x is just 2 sine x. And as for the denominator, we can write it out again. Okay, so let's stop for a moment. We now have one fraction, which is sort of what we were hoping to get. But that one fraction doesn't quite look like the right side yet. Notice that we actually have the 2, so see we have the 2 over here, which is there as well. That should give you some confidence that we're on the right track, but we still have to keep simplifying this in order to somehow make it look like the right side. So what haven't we done yet on the left side? The only thing we haven't done yet was FOIL the denominator, so I'm going to actually recommend we do that now. Alright, so here we go. 1 multiplied by 1 is 1. 1 plus sine x is sine x. Negative sine x multiplied by 1 is negative sine x. And negative sine x multiplied by positive sine x is just negative sine squared x. Remember, that's the way of conveniently writing sine x all squared. You can go ahead and collect like terms, so the sine x's cancel, leaving us with 2 sine x over 1 minus sine squared x. Somehow we have to make the denominator look like a cosine x. Where have you seen 1 minus sine squared x before? I hope you recognize that 1 minus sine squared x, if you look at the table of identities, it's just cos squared x. Now we have our cosine there, but it doesn't quite look like the right side of the original expression. So what can we do here? I'm going to do a trick. Instead of writing cos squared x, I'm going to write this as cosine x multiplied by cosine x. And the reason I chose to do that is I have the cosine x that I'm looking for, and guess what sine x over cosine x is? I know you've seen it before, but I hope you recognize that sine x over cosine x is just tan x. So we're done, everyone. This is equal to 2 tan x all over cosine x. We use substitution over here, and therefore we've shown that left side equals right side. Okay, I lied. I said that was a medium identity. I think that was a slightly harder one. And listen, if you have to replay the video, watch it again, I don't blame you. I'd actually recommend you do it on another sheet of paper if needed. But please go ahead, listen to my steps as I go. I hope it was clear. And again, ask questions if anything is unclear. Let's do another one. Okay, this one is a medium-ish identity. So we have to show that 1 minus cos squared x multiplied by 1 plus 1 over tan squared x is equal to 1. Don't start with the right side. If you do, there's really nothing to do with it. Please start with the left side. Remember, we always start with the more complicated side. Okay, so what operation are we doing over here between the two brackets? The operation is multiplication. So something that looks very tempting is to FOIL the brackets, and I don't blame you, but before you do that actually, I'm going to make a recommendation. Where have you seen 1 minus cos squared x before? I hope you recognize that as sine squared x. So let's make that substitution right away. Okay, another thing I want to mention at this point, everyone, is when you're working with identities, sometimes you just have to be willing to try something. What I mean is, there's really no rules for these in the sense of do this, then that. Identities are different from everything you've ever done in mathematics because there isn't a script to follow. So this is where you have to be willing to play with it. By play with it, I mean be willing to just try things, and it's like a puzzle. You have to keep working with one side until it looks like the other. In all honesty, have fun with it. It's going to be frustrating at times, but for me personally, I loved learning these. It was a challenge. I have to work with one side and somehow try and make it look like the other one. For those of you who like a challenge, this is really for you. All right, so with that being said, how can I make the left side look like 1? Well, the only thing really left to do is to try and simplify this. So I'm going to go ahead and FOIL. So sine squared x multiplied by 1 is just sine squared x. Sine squared x multiplied by 1 over 10 squared x is just sine squared x over 10 squared x. All right, so this doesn't quite help us yet, but we're adding two fractions. Sine squared x is over 1, and we somehow have to make these two fractions add up to 1. So the only way to do this is to literally add the fractions. And when you literally add the fractions, you need a common denominator. So I'm going to multiply the first fraction by 10 squared x over 10 squared x. Okay, and we're still adding the other fraction, which is sine squared x over 10 squared x. Okay, so we have a common denominator. Let's go ahead and add the numerators. So this is equivalent to sine squared x multiplied by 10 squared x plus sine squared x all over the common denominator of 10 squared x. Okay, so with that being said, let's see what we can do in the numerator. I see a greatest common factor of sine squared x. So I'm going to go ahead and factor the sine squared x out of both terms in the numerator. That gives me 10 squared x plus 1, which is still all over 10 squared x. Where have you seen 10 squared x plus 1 before? This expression looks familiar to me. Let's go back to the table on the first page for a moment. And there we go. Look at the second last identity. Here, let me clean this up a little bit. One moment. Look at the second last identity. 1 plus tan squared x is equivalent to secant squared x. Let's make that substitution. So this is sine squared x multiplied by secant squared x all over tan squared x. Okay, we're almost there. We have to make this equal 1. Watch this. What's secant squared x? I hope you recognize that secant squared x is just 1 over cos squared x. So I'm going to write this as sine squared x multiplied by 1 over cosine squared x. And I don't like fractions over fractions, so I'm going to use the division symbol here. So we have sine squared x multiplied by secant squared x, which I replaced with 1 over cos squared x, and all of that is being divided by tan squared x. Hey, what's sine squared x over cos squared x? Well, hey, sine x over cos x is just tan x. So sine squared x divided by cos squared x must be tan squared x. So we have tan squared x divided by tan squared x. And guess what? Tan squared x divided by itself is just 1. And that's done. So therefore, left side equals right side. Do you see what I mean by having to play with these a little bit, just working with them, trying out different things? Let's continue practicing. All right, example 5. So we have to show that sine x to the exponent 4 take away cosine x to the exponent 4 equals sine squared x take away cos squared x. Let's start with the more difficult side, which I think you'll agree is the left side. Okay, so now we're subtracting two expressions. And where have you seen something like this before? You've seen something like this when you were factoring. Do you remember a difference of squares? For instance, if we had, let's say, x squared take away y squared, that can be factored as x plus y multiplied by x minus y. Similarly, if you had x to the exponent 4 take away y to the exponent 4, that would factor as x squared plus y squared multiplied by x squared minus y squared. And notice, this is just another difference of squares which can be further factored again. But my point is, oh, sorry, I just caught a little typo here. That should have been y to the 4th. But anyways, my point is, this is just a difference of squares. So let's factor it like that. We have sine squared x plus cos squared x multiplied by sine squared x take away cos squared x. All right, compare to that with the right side. So it looks like we have the thing we want. We have the sine squared x take away cos squared x. That just means we somehow have to get rid of sine squared x plus cos squared x. Do you remember what sine squared x plus cos squared x is? It's an identity. It's just 1. So you can replace that with 1. So that's 1 multiplied by sine squared x take away cos squared x. And anything multiplied by 1 is itself, so we're pretty much done. All right, so therefore left side equals right side. So that one was a little easier, I guess, but you definitely had to recognize the difference of squares to do it. And I believe we have one more to go, example 6. Okay, so this would be another sort of medium to hard one. I'm going to recommend that we work with the left-hand side. We actually did a very similar one back in example 3, I believe. I think we had sines and cosines though, rather than cotangents and cosecants. But the idea is the same. You have to take these two fractions on the left side and somehow make it look like one thing. The only way to do that is to find a common denominator. So I'm going to put brackets around the expressions in the denominator like so. And we need to multiply each fraction by what it's missing in order to have a common denominator, which will allow us to add the fractions. So let's do that. This is equal to cotangent theta over cosecant theta minus 1. We're going to multiply by cosecant theta plus 1 over cosecant theta plus 1. We do the same thing with the other fraction, so we have cotangent theta over cosecant theta plus 1. Let's multiply the top and bottom of the fraction by cosecant theta minus 1. That's the thing that it's missing. Okay. I think I may need to make this a little smaller again, just to make sure I have room. So give me a second. Okay. All right, everyone, so it looks pretty good. So let's go ahead now and multiply the numerators. So this is cotangent theta multiplied by cosecant theta plus 1. Don't mind me, I'm going to go to the big fraction step just to save some room. So we add the numerator of the other fraction, which is cotangent theta multiplied by cosecant theta minus 1. And that's all over our common denominator of cosecant theta minus 1 multiplied by cosecant theta plus 1. Okay, so now that we have a common denominator, let's simplify the numerators by collecting like terms. Don't FOIL the denominator just yet. We may have to later as well though. So if I distribute in the numerator, we're going to have cotangent theta multiplied by cosecant theta plus cotangent theta, okay, just using the distributive property, plus cotangent theta multiplied by cosecant theta, take away cotangent theta, which is all over our common denominator, which I'll just rewrite for now. Okay, so you can definitely start cleaning up the numerator. Add like terms. Notice that we have a positive cotangent theta, which will cancel out with the negative cotangent theta. And we have cotangent theta multiplied by cosecant theta. You can treat that as a like term. So we're going to add up these two terms over here. How many of those do you have altogether? Treat it just like you're collecting like terms. You have 2 of them. Okay, what I'm actually going to do now, just to save a little bit of room, is FOIL the denominator, okay? So here we go. Cosecant theta multiplied by cosecant theta is cosecant squared theta. Cosecant theta multiplied by 1 is just cosecant theta. Negative 1 times cosecant theta is negative cosecant theta. And negative 1 times positive 1 is negative 1. Collecting like terms, you can get rid of the cosecant theta and the negative cosecant theta. And this is going to simplify to 2 cotangent theta multiplied by cosecant theta all over cosecant squared theta minus 1. We are almost there. Where have you seen cosecant squared theta minus 1 before? Let's go to the very first page for one moment. And if you look at the very last identity, if you bring the 1 to the right-hand side, you get cosecant squared theta minus 1, which is equivalent to cotangent squared theta. So basically, I'm going to replace cosecant squared theta minus 1 with cotangent squared theta. Let's do that. All right, so I'm going to continue up here. I should have enough room. So that's 2 cotangent theta multiplied by cosecant theta all over cotangent squared theta, which I'm going to write as cotangent theta multiplied by cotangent theta. Look what happens. Cotangent theta cancels out, leaving us with 2 cosecant theta over cotangent theta. And we have to show that this equals 2 secant theta. So we're almost there. Recall that cosecant theta is just 1 over sine, and cotangent theta is the reciprocal of tan. So we can write this as 2 times 1 over sine theta divided by cotangent theta, which is just sine over cos. All right, let's multiply by the reciprocal. So actually, I may have to go to the next page just to make sure I fit this all. If you need a little more room, feel free to write on another sheet of paper. So we have 2 over sine theta multiplied by the reciprocal, which is cos theta over sine theta. Sorry, I made a mistake here, didn't I? 1 second. Okay, here's my mistake. I replaced cotangent theta with sine theta over cos theta, but what I meant to do was replace that with cosine theta over sine theta. Sorry about that. Because remember, cotangent is just the reciprocal of tan, so instead of sine over cos, it's the reciprocal, which is cos over sine. So I need to multiply by the reciprocal of that fraction now. So instead of dividing by cosine theta over sine theta, we multiply by sine theta over cosine theta. And look what happens. We cross-reduce, the sine thetas cancel out, which simplifies to 2 over cosine theta. Well, what's 2 over cosine theta? That's just 2 multiplied by secant theta, which is the reciprocal of cosine. And just to compare it, that's our right-hand side. So we're done. Okay, so therefore left side equals right side. That was a tough one. Okay, so once again, my apologies for that mistake earlier, but I knew it wasn't working out, so I went back quickly and checked. Now, I did assign you some homework from the textbook, but I'm going to recommend instead of doing this, I posted a worksheet on our course website for you. So do the worksheet instead. If you find you still want more practice, then go ahead and complete the questions from the textbook, but in all honesty, I think the worksheet is more than enough. If you have any questions, don't hesitate to reach out. Thank you everyone. I'll see you in the next video.